For this sample problem, we are going to be looking at our structural steel structure for the first time. So we are doing a problem set related to figuring out the actual weights of the columns, since steel is bought and sold based on its weight. So we'll look at the columns, we'll look at the beams and girders, and we will also look at our floor joists, all made out of different forms of steel. And then we'll lastly look at our metal decking for all of our material costs. All of our materials. Then we will look at the material cost, figuring out how we can then apply the pricing to all of the different items that we have been taking off and finding quantities for. So we'll find per unit cost, we'll find also total cost for the different materials, and then the overall total cost for the entire structure. So first off, let's just take a look at our steel structure. There are both hand drawings as well as electronic drawings provided on Blackboard for you to reference. The electronic drawings are a little bit easier to read. However, there are some errors in the actual drawings themselves. So I will be referencing our hand drawings at this time when we're going through our materials. So we have our basic foundation plan. We have floor plans, then we get into our framing plans that list out all of the different structural steel elements as well. We also have our second floor or roof framing plan, and then we have bill of materials and some details on the beams themselves. I will be referencing some other drawings as we go through the sample problem that are included on Blackboard Learn for your reference. So starting off, we are going to look at the weight of one column. Lucky for us, if we go and we look at our bill of materials, it will tell us the exact height of our columns. So here in our bill of materials for our columns, we see that we have different ones, and that deals with the different configurations that we have of the beams and girders coming into them. But if we look at our bill of materials, we can see that we have W8 by 10 columns, and they are 14 feet 7.5 inches. So the length of each one is 14 feet 7.5 inches. If we did not have this information on the bill of materials, and if we did not have an actual dimension provided to us, we can figure out what that height is by using the elevations of our plans, but thankfully we don't have to do that in this problem set. So once we have our length of our column, we know also that we have W8 by 10 is the steel I-beam that we'll be using for the columns. We'll just be setting them up on end. So the first number, as you recall, is the depth. So if we're looking at our I-beam, we're talking about the depth being 8 inches. The second number, that is the pound per foot of the steel. So it's very easy when we know the length and we know the weight per foot to calculate what the weight of one column would be. We put our 14 feet 7.5 inches in decimal form, 14.625 feet, multiply that by 10 pounds per foot, and we end up with 146.25 pounds. If you want, you can round it up, 147 roughly, for each one of the columns that we will be using to build the structure. Number 2 then asks, what is the total weight of all of our columns? So this is simply figuring out how many columns we have, and then we are going to multiply that by the weight of each individual one. It's a simple counting item at this point because we don't have that many. It could be a repetitive member item if we had a very large structure with a lot of columns, but we can simply look at this and see it's a grid pattern. We have 4 running along the top, 4 running along the side, and therefore we have 16 columns that are making up this structure. So 16 each, once we've counted them, multiply by our 146.25 pounds, and we get 2340 pounds as the weight. If we wanted to, we could convert it to tons. At this point, leaving it at pounds is fine, whichever one we would like to do. Number 3. Now we are getting into the beams and girders of our plans. So if we look at our second floor framing plan, our beams and our girders are what connect each column together. We also see that we have our joists that are running between our beams, but again, just between the columns is where we have our beams and girders. Then also, on the roof framing plan, we see we have the beams and girders in between each of the columns, but we also have a beam that is connecting the beam to the beam, so we have additional ones on our roof plan. But for now, we're looking just at our second floor plan and figuring out the beams and girders for that. There are different lengths of our beams and girders that we are going to use. So this is in reference to the sketch you will be required to do for this week. But if we have 2 I-beam columns that are setting up on end, and we have our beam or girder running across, if it is connected from center to center, then that is going to be the full distance across, which per the plans is 7 foot 4 inches. However, some of our configurations have our I-beam in this orientation. Some of them then are 90 degrees from that. So the connection then is from the center over to just the edge of the I-beam. So as we set up here, we have 8 inches for our depth of our I-beam. Half of that then, if we're going to look at just a partial, that is going to be 4 inches, half of 8 inches, meaning this dimension down here is also 4 inches. It is half of that depth. So if we want to then dimension this second length of beam or girder, we can see that is 7 foot 4 less 4 inches, or 7 feet. Lastly, we could have them configured, both of them in the horizontal orientation, with our beam or girder coming between the two, meaning we are only looking at this dimension. We've already established that we come in 4 inches on this side, but we also have to come in 4 inches on the other side. Therefore, the length of this one will be our 6 feet 8 inches. So we have 3 different lengths of beams and girders that we have to deal with. And we want to figure out what our average length is when we total all of them up. So if we look at our plans, and these are posted on Blackboard to help you reference, if we're looking at our second floor framing plan, our 6 foot 8 beams run along the middle of our structure. So simply counting 1, 2, 3, 4, 5, 6. So we have 6 that are 6 foot 8. Next, if we look at our 7 foot beams, we can see them in these configurations here. They're running along the top bays and the bottom bays as well. So simple count, we see that we have 8 of these quantity. So we have 8 of our 7 foot beams. Lastly, the 7'4", they run along the top, they run along the bottom, and then we have them going in the 90-degree to those original ones that are in the center of our structure. So totaling all of these up, we can see we have 10 at the 7'4". So at this point, we just calculate an average. We're looking at 10 of them at 7'4", 8 at 7 foot, and 6 at 6'8". If we do that math, this is still part of number 3. We have 7'4", 10 of those. We have our 7 foot, 8 of those. And we have our 6'8", and we have 6 of those. Total lineal footage then is 169.3 repeating. If we divide this by the quantity, which is 10, 8, and 6, means 24 total. 7.0556, or roughly 7.06 feet, is the average length of the beams and girders for our second floor. This just helps give us a quick count and a quick dollar amount when we figure out what is a cost per unit, and we can then apply that across the board rather than coming up with 3 separate numbers. When it comes to actually purchasing, then obviously we will need to know the differences, but for a quick estimate, we just want to find the average. From this, we can then find the total weight for all of our beams and girders for the second floor. We can take our 7.06 and multiply it back by the quantity to get the total. But since we already have the total lineal footage, this is the lineal feet multiplied by our 10 pounds per foot. The beams and girders for the second floor are also W8 by 10. So it is the second number that is our weight per foot, and we get 1693.3 repeating, or roughly 1694 pounds. For number 5, we are looking at our joists for our structure. So just like with our second floor beams and girders, we have 2 different lengths. We'll have ones that run from center to center, and then we will have ones that run from center and then out past. If we wanted to see what that means, is if we have our beams sitting across here, if we had a joist, it would sit across, come across down the bottom and back up, and this would be in some sort of web configuration. But this is for the center. If we have one that needs to run to the outside, it would start at the center of the I-beam as well, run out, but this will come all the way to the outside of our structure. We need to make sure that our decking extends all the way to the outside, and this is where we looked through our plans, we could see that it only goes from the center all the way to the outside, whereas here it's center to center. So the center to center ones are going to be our 7 foot dimension, and the center to the outside will be our 7'4" dimension. I apologize, it's 7'4" and 7'8". The center to center, like we had before, was 7'4". So if we have our quantities that we're looking at for the 7'8" joists, we have 9 running along the top, 9 running along the bottom. That is 18. For the 7'4", we can see we have 6. So 7'4" times 6 plus the 7'8" times 18 gives us 182 lineal feet of joist. Divide by the 24 quantity gives us 7.5833. So 7.58 roughly feet is the average per joist. If we are looking for the total weight, then we see in our sample problem that we have 8.5 pounds per foot. Unlike when determining structural steel, and it tells us that we have 8 by 10, the configuration for the joist does not tell us anything related to the weight per foot. So we have to know or look up at a table what that weight per foot is. But if we have our 182 total lineal footage times at 8.5 pounds per foot, so again, this is given to us, we can total up and see we have 1547 pounds as the total weight for our steel joists. For number 7, we are now looking at the roof framing plan. So if we look at these drawings, we can see very much similar configuration to the second floor. We have the same location as the second level for our 6/8 beams. So we have 6 of them that run along the center. Also, same for our 7-foot beams, 8, so 4 running across the top and 4 running across the bottom, again, same as our second level. Where it changes is when we get to our 7'4" beams. So the orange ones show the same location as what we have on the second floor framing plan, but the additional blue show where on the second floor we have our joist, but here we have our additional beams. So we have the same 7 foot, 8 of those. We have the same 6'8". We have 6 of those. But now for our 7'4", we have a total of 19. So 9 additional to the 10 that we would have had on the second floor. 235.3 repeating divided by our total quantity of 33 gives us 7.1313, or roughly 7.13 feet. So let me rewrite that, 7.13 feet. So that is the average length of the beams and girders for the roof. Coming up with that total weight, these are again W8 by 10, same as the second floor and the columns. So it is the 235.33 repeating times the 10 pounds per foot. We get 2353.3 repeating, or 2354 pounds. So we've calculated the weight for all the columns, all the beams and girders, and all of the joists within the steel structure. The only thing that's left is our decking. So number 9, we are looking for the square footage of our decking. So we need to understand where the decking goes before we can calculate this. If we're looking at our second floor framing plan, this is where our metal decking is going to go. It sits on top of the joist. It is not in the center of our structure. Per the floor plan, this is where our stairs are going to go. In actuality, when we build this in our lab, this is where our crane is located. So we need to make sure we don't put metal decking in the center here. So if we look at our overall dimension, we see we have 22 feet. But again, that only goes from the center of the I-beam to the center of the I-beam, or in this case, it's up on end, so it's the column. So when we're looking at the overall where the decking goes, recall from our joist length calculation, we have to go to the outside. So we have to add the 4 inches on this side and add the 4 inches on the other side. So overall, our structure is 22 foot 8 inches by 22 foot 8 inches. Then we need to subtract out the opening. If we just simply look at our dimensions, see our 7'4", that is again if we go from center to center. But we need to pull our decking over to the edge, to the end of the I-beam. So in this case, we actually need to subtract the 4 inches from each side, because we have to go from center over to the edge, center, in. So we have 4 inches subtract on this side, 4 subtract on this side. So from our 7'4", it's actually 6'8" by 6'8". And that is for our opening. If we do the multiplication, subtract it out, we have 469.33, so roughly 470 square feet of decking. The last problem is a little bit more intricate. It says we have 8 foot by 3.5 foot metal decking pieces. So similar to OSB or another type of plywood, instead of having our standard 4x8, metal decking can come in different widths and lengths, so we are given the dimensions for that. It also says that we have to have 6 inches of overlap. So we need to figure out the total square foot of decking panels to be purchased. Similar in concept to our roof felt, when we're dealing with overlap, we have to look at overlap for our decking panels. So our decking panels are corrugated metal that looks similar to this. When we have to place the second panel, we can't just pick up from here and go. It will not lay correctly. So typically there is some overlap before it continues on with the second panel. This, per our specifications, is 6 inches. So this is in both directions. It is our width-wise as well as our length-wise. So if we are looking at our panels in terms of squares or rectangles, it means that this second one will come over like so, but also in the other dimension, it will overlap. So it's that 6 inches in each dimension. So it actually shrinks down our coverage area a little bit. So the actual square footage of each panel is 8 feet by 3'6". That's what's given to us. So that is 28 square feet. But our coverage will be 6 inches less on each one of those. So it's 8 feet minus 6 inches by 3'6" minus 6 inches. From that, we can calculate that it is 22.5 square feet. So if we take our total square footage and divide it by the coverage square footage, it is the 22.5 square feet, because that is what is actually covered by our decking. We get 20.859. Round that up. We have 21 panels that we need to purchase. However, I ask you for the square foot of panels to be purchased. So we have to take the quantity and in this time multiply it by the actual square footage of each one. 588 square feet is our final answer. So what this is saying is we need to purchase 588 square foot of decking in order to cover 470 square foot of decking area. And that concludes the sample problem for calculating our decking materials.